So by definition, the rank of a matrix is the number of rows it contains that are not all zeros when brought to row echelon form. This is one way to define rank. So to clarify, let's make an example. So here's a 4x4 matrix, and generally there's no immediate way to tell the rank of such a matrix. So we need to reduce it to its row echelon form. We can let Mabel do that, and the result is this matrix. And as you can see, there are 2 rows of all zeros, and there are 2 rows that are not all zeros. So by definition, this matrix has rank 2. Obviously, for such a 4x4 matrix, the maximum rank is 4. And because it doesn't have the maximum possible rank, we call it a rank deficient matrix. Notice that the rank of the matrix is independent of the row transform we have performed. So this matrix over here actually has rank 2, and so does this matrix. So the rank doesn't change under the Gaussian elimination. Now let's try another example. Here's another matrix. It's almost the same as the first one. I just changed a few numbers, this number and this number. And let's investigate the rank of this matrix. It actually turns out that when reduced to row echelon form, it looks like this. So by definition, this matrix over here has rank 4 because there are no rows in this matrix consisting of only zeros. We say that this matrix has full rank. There's another way to look at this. Notice that when we transform this matrix into its row reduced echelon form, what we do is a Gaussian elimination, and that's basically the same as solving this equation, in which we're trying to find the 4 values of k1, k2, k3, and k4, so that k1 times the first row vector here plus k2 times this row vector plus k3 times this row vector plus k4 times this row vector equal the 0 vector over here on the right hand side of the equation. In other words, this is the equation we're trying to solve here. And it turned out that the solution looks like this. So if I am to write it out, then the solution for k1 is minus 2 k2, and the solution for k3 is minus 2 k4, and as for k2 and k4, we don't know anything, so they're just free parameters. k2 equals k2, k4 equals k4. So that means that we have a double infinity of solutions. As you may recall, Having solutions to this problem means that these vectors here, if we conceive the columns in the matrix as vectors, they must be linearly dependent. And as it turns out, if you take a look at the reduced form of the matrix, this vector here is linearly dependent of this vector, or the other way around, you may say. And these two vectors here, these two column vectors, are also linearly dependent, whereas these two are independent of each other. So altogether we have two linearly independent vectors in this matrix. So as it turns out, the rank of a matrix equals the number of linearly independent vectors, column vectors. We won't prove this here, but it's worth noting. As for the other matrix here, it's pretty obvious that it contains 4 linearly independent vectors here. If you can't remember what that means, please revisit the video on linear dependence. So you may define rank as either the number of rows in the matrix in the reduced echelon form that are not all zeros, or as the number of linearly independent column vectors in the matrix.